the cloud. And this will be available and posted on YouTube after class is over. All right. So we're starting off with the parametric form of a derivative. And you see these lovely looking formulas. One of them, dy dx is equal to all that stuff. And then d2y equals dx squared. That's another beaut. But that one's incomplete. All right. And so the rationale here is if we're thinking that we're given a form of a parametric equation represented as x equals f of t, so x as some function of t and y is some function of t, we'll call it g of t, call it whatever you want, as long as there's a t in it, then to find the derivative dy dx, it's pretty reasonable to say that if I just take the derivative of this guy, I could say dx dt is equal to f prime of t. And then I could say dy dt is equal to g prime of t. All right. But then the big concern is that, okay, well, all right, that's all good, but how do I get a dy dx out of that? And so that's where this more elaborate approach comes into play. So what it's really telling us is that if we take dy dt and divide it by dx dt by rules of complex fractions, the dy dt's cancel away, and you're just left with dy dx. Right? So as long as dx dt isn't equal to 0, that's a statement regarding domain. As long as dx dt isn't equal to 0, then your dy dx will exist. All right. So another form of this, so we now know that we could represent dy dx as dy dt over dx dt. But we also know that dy dt can be thought of as, if we're defining x as f of t and y as g of t, we can also say g prime of t divided by f prime of t. All right, so there's a few different variations of the derivative of a parametric form of a function or an equation, right? Now, that's all well and good. It doesn't really have much meaning to us until we actually do something with it. So, you got to be a little patient when it comes to this, because we do the foundational stuff first, and then we get into, okay, now why did we do all that, right? So just kind of bear with me on that. Because the second part involves us finding the second derivative, right? So when you think about a second derivative, and this goes all the way back to Calc 1, and it's interesting because I teach my high school calculus class. It doesn't always boil down that I'm teaching Calc 3 and introductory calculus at the same time, but when it does, it almost feels like whenever I'm teaching a concept in Calculus 3, I'm teaching the origin story to that in calculus, like on that day. It's kind of weird. And so we're in calculus today, we were talking about where that notation for the second derivative comes from. Why the 2 comes after the d on top, but it comes after the x on the bottom. And that has to do with the fact that we have this idea. So what does that mean? Well, if I were to say something like, I want to find the derivative of y with respect to x, right? So I'll just chuck that off on the side here. The derivative of y, dy dx, is really the same as saying d dx of some function y, all right? Whenever we're taking a derivative, it's always, with respect to x, it's always d dx of something. That's why we're able to say things like d dx of x squared, because if I say, for example, so if y is equal to x squared, then by substitution, I would be saying that we're really looking at d dx of x squared. All right. I don't know what your experience was in the early calculus courses, but I found whether as a teacher or students that have come from other teachers, that idea has kind of been glossed over. Like why do we say d dx of sometimes? Why do we say prime sometimes? Why do we say dy dx sometimes? And so in this course, the notation is going to become more and more important because when we get into partial derivatives, we're going to have to distinguish one type of derivative from another, right? And so we got to be really careful about that, right? So in this context, what I'm saying when I'm talking about a second derivative is that I'm taking the d dx of my derivative, right? So that's where this notation is coming from. So when I'm looking at this, I'm saying, okay, I got my derivative, which is dy dx. I'll highlight that. It's got all these equivalent relations, dy dt, dx dt, all that good stuff. But that boils down to some quote unquote function. It's no more impressive than a y function. In fact, dy dx is just a rate of change associated with y, but it itself is typically a function. All right. So what I'm saying is, well, let's take the derivative of that. And if we do, notation wise, just looking at the algebra of it, well, what do I get if I take d times d? D times d is d squared, right? So that's where our d squared comes from. And then on the bottom, if I bring it in a little bit, I'm taking the entire dx and multiplying it by dx. So that's giving us dx squared, right? So here it's just the d's being multiplied. So that gives us the power of 2 with the lone y at the end. Whereas on the bottom, we're actually multiplying the dx's together. All right. Is that important? Yeah, it's going to be more and more important. The notation is going to be a heavy emphasis of this course. So I don't want to gloss over even the early stuff. All right. And you may look at that and say, well, isn't that a prereq thing? Shouldn't that go in the Unit P video? Honestly, maybe it's in there. I don't remember, but it's not. That was more of the pre-calc stuff. This is more like, let's talk about the calculus too. All right, so what are we doing here? We're taking d dx. Let me get a thicker marker here. D dx of what I stated earlier is dy dx, all right? So that would be this expression. So that's in essence what we're looking for, all right? So this is where it gets weird because what we're dealing with here is a brand new y function, all right? So we have a brand new y equation. It serves a different, it's taken on a different role, but it essentially has the same underlying concept, right? So I'm going to rewrite this a little bit, and it's going to seem like a waste of time, but hopefully you won't really feel that way. All right, so I'm going to rewrite this. And I'm going to make it like super small. I'll zoom in, but just to get it in there. All right. So this is basically a brand new dy dx. All right. It's just this whole thing, this whole shebiggy bang here is taking on the role of the y. All right. So that's where that notation is really taking shape. Because now I can go back to my first derivative model and say, okay, I got dy dx, right? Where this whole expression is that little y right there. So everywhere I have a y, it gets replaced with this whole expression. All right. Everywhere I have an x, I'm going to go with a fresh new highlight color. Everywhere I have an x, it's still an x. It doesn't get replaced with anything. It stays as an x. So what we would get here is, right, dy dt. So d, all of that stuff on the top, And so I'll rewrite that. See if I still have it saved. I do. Shrink it. Over dx dt. All right. So it's telling me to take the derivative of my derivative, the same one I got in that first step, but then divide it again by my dx dt. All right. Very weird, but very doable, because now I can think of, okay, I got my dy dt over my dx dt. I can go back and forth. I can think of that interchangeably, because this would be the same as saying, I'll do a quick whoa. And wipe this out here, because we know dy dt over dx dt is really the same as saying dy dx. So it's telling me to take the derivative of my first derivative with respect to t and then divide it by the derivative of the x equation with respect to t. All right, so really, really interesting stuff. So what I'll do here before getting on to the arc length stuff is we'll flip to the next page, try an example or two, and then we'll come back and dig into some other stuff. All right. So, but that's the notation component, and there's a lot of detail there. I can tell you that early on in my education and even in the teaching, I really was more of a, here's a rule, let's follow the rule. And the more I, sat down to really think about why the rules worked the way they did, the more I started to understand math, in a more holistic sense. And things started, it's sort of like the mind blown, people say that. It's not quite like that. It's more like mind expanded. You start realizing, oh, there really is a deeper meaning to all this stuff. And once you realize that, it gets more and more interesting. That's the thing. You don't run out of applications to this stuff, because your brain will constantly find newer and newer ones. All right. Well, actually, I did want this over here. All right. So let's hop to the next page. Figured I bought you enough time to copy that down if you needed to. I took the liberty of copying and pasting the rules on here because, best laid plans, there are some folks that would absolutely love to understand the underlying rules, but you do need some time to digest it. For now, work with the formulas, and then when you understand, you look at the rules, you look at the formulas, but if you want to understand the underlying concepts behind the rules, it's going to take some time. All right. So we buy ourselves time by relying on a rule early on and then going from there. All right. So number one, simply asking us to find the derivative and the first and second derivative with respect to x. So the first thing I would want to do is rewrite my x equation as 2t to the 1/2 power. All right, my y equation is fine the way it is. I'm going to take the derivative dy dt. All right, so I'm working with this one first. And the question might be why? Well, eventually I'm going to divide that by dx dt. And the way I tend to organize it, I'd like to have whatever my numerator is going to be first, then below that, whatever my denominator is going to be, and then the actual quotient. So it's just an organizational strategy. So we're looking at 6t minus 2. For the dx dt, that one's a little easy. Well, they're both equally difficult. Question?
Yeah, we will have t for dx dt.
Say it one more time.
We will have t for dx dt. Doesn't we?
The dx dt is going to be, are you asking or I can't quite hear you. I'm sorry.
No, actually, I tried to answer it. Never mind. Just finish.
Oh, okay. Apologies. I didn't quite grab that. Yeah. So when we take the derivative, we're looking at t to the -1/2. Is that what you said?
No.
Yeah. So folks, feel free to chime in at any time. I apologize. Sometimes I get into a kind of a groove, and especially when I'm looking at the blank screens, because I'm like, oh, I'm the only one here. So yeah, definitely feel free to chime in. If you want to make your voice heard, you're always going to be welcome to do that. All right. Now, dy dx, that's going to be not too bad now, because all we have to do is take our dy dt, 6t minus 2, and put it over the t to the -1/2, and that's our dy dx. Now, because I have to do something else with this, it might be a good idea to simplify it a little bit. It's one of those things where you make a choice, and then you either are glad that you made a particular choice, or you regret it later on. You'll find out, right? So what I'm going to do is I'm going to split this fraction up. So I'm making the choice to simplify, in case anyone was wondering. So 6t over t to the -1/2 minus 2 over t to the -1/2. Something to bear in mind, folks, and this is a good rule of thumb to have for this class. Just remember, whenever you're thinking about the amount or type of work that you need to show to solve a problem, just reflect back on the title of the course. All right, calculus, not algebra. All right. So I don't need to see the algebra steps. I do need to see the calculus steps, right? So if there's some algebra steps that, any ordinary student would be able to perform in their head, then you don't need to show the work for that. Now, if it's something like, I don't know, sine cube t minus tangent raised to the 7th power, and you're using Pascal's triangle to expand that out, yeah, you probably got to show some details, but that's pretty rare. All right, so keep the base, subtract the exponents. So 6t to the 3/2 minus 2t to the +1/2. And I would recommend leaving it like that, because that's power rule ready. All right. So when we get to our second derivative, I'm going to take the derivative with respect to t of my first derivative, dy dx, and then I'm going to divide that by dx dt. The good news is, for a problem like this, we got a lot of this work already tackled. Most of the hard work is already done. All right. The derivative of dy dx. Okay, so again, dy dx is what we get when we simplify this. Well, we had it a while ago, but we chose to simplify it because it was going to make our life easier. Because, I mean, just think about it. Power rule versus quotient rule. You want power rule, I would imagine. Quotient rule wouldn't have been too hard in this case, but it's still, the algebra was easier than the quotient rule would have been. All right. So the numerator is going to be, we're going to multiply 6 by the 3/2, so it's a 9 t to the 1/2 minus t to the -1/2. That's up top. All right. So just double checking, because that's kind of thing I usually screw up, the simple stuff. The denominator is just going to be dx dt, which we already know is t to the -1/2. Now, this is one of those situations where you could actually leave it. Now, I can tell you that I will never ask you to simplify unnecessarily. All right. So a question like this, I'm not going to tell you to simplify, because you'll know you want to simplify the first derivative before starting the second derivative. When you get to the second derivative, you could leave it like this, because what would be the benefit in simplifying? We're not doing anything with this. It's just a demonstration of skill. Everything after this would be algebra. Now, if you can't stop yourself, that's, you know, that's a different story. It actually cleans up kind of nicely, you know, because if you break it up, 9t to the 1/2, and again, you don't have to show the step of breaking it up if you can just do it in your head. I have a rule. It's I call it, it's a no intelligence penalty. Not like a no intelligence, but like there is no intelligence penalty, right? So if you're smart enough to do certain things in your head, then I'm not going to penalize you for that. All right. Lord knows enough of us have lost enough credit over the years because of that sort of thing, right? But the only thing is, if you did so much in your head that any teacher would look at it and say, I'm not sure if you did it in your head or you cheated, then you probably want to show some work. All right. So keep the base, subtract the exponents, 9t to the 1/2 plus 1/2, so to the first power, so 9t. And then minus a 1, because anything divided by itself is going to be equal to a 1. Right. So kind of surprising that it came out so nice, but you know, in the end, okay, it's just an answer. So what did it matter what form we left it in? You know, that's always going to be part of the challenge, making that decision. All right. So what does this mean? Good question. Nobody knows. Like the brightest people on the planet have no idea what this is. That's not true. There's a reason why we're learning it. All right. What we have here is a slope of the line tangent to the curve at any point along the curve. So then the big question is, okay, well, how do I get this curve? Because we've been staring at this Desmos calculator that does a really wonderful job of understanding functions in the form of y equals something in terms of x, you know, very nice. But what about something like y equals t? It really thinks that t is an x. You know, what if I typed it in this way? I'll show you. This is the wrong way to do it, but let me just show you. Let's say I did y equals 2 radical, and then I used the t. All right. So Desmos thinks that this is part of a parabola, right? Because what it's doing is it's solving for t kind of on the fly and giving you, what would that be? 1/4 y equals 1/4 x squared, right? So that may or may not be what the function is, but it didn't account for the y. I could put the y in there too, but it's going to give me a separate equation. All right. When we have parametrics, it's two equations that give in 2 dimensions. It's 2 equations that give us one curve, right? And what's happened, or what has happened behind the scenes, is that you had originally an equation where it was solved for y in terms of x, maybe, or solved for x in terms of y, or maybe not solved for either of them, but it was in terms of x and or y. But a new parameter, a new variable was introduced, t, typically referencing time, but not always, that was introduced to give us not only location, but the moment in time at which a point on the curve is at that location. You know, because think of it this way, you can draw a parabola, but what if I said, okay, at what time are you at the point 1, 1? Now, if you're in a regular algebra class, your answer to that might be something like, I don't know what the hell you're talking about, dude. Like, are you talking about like when I started drawing it? Like, okay, well, it was like noon when I started drawing it, and when I finished, it was like 12:01. Okay, so I guess 1 minute. You're not wrong. You know, that would be a particular reference of time, but maybe not the one I was looking for. Right. But the idea that you're introducing a time component is important, but it also it is important, but it also involves designating what time t equals 0 means in the context of a problem. So the fact that this question has no context tells us that, well, you know, we got nothing, you know. However, we can still get an idea of what the path is going to be, right? So we can get this curve plotted just based off of knowing the fact that x comma y, what we thought of as coordinate values, can now be thought of as function values. All right. So we can write coordinates that are made up of equations. Well, really just the right-hand side of the equation. My t looked a little off there, so I'm fixing it. Right? So I can put in, instead of just x equals 2, y equals 1, 2 comma 1, plot the point. Instead of doing that, I can now say, well, x is an expression in terms of t. I can say 2 rad t, comma 3t squared minus 2t. Poor quality close parentheses. Let me square that away real quick. All right. And the great thing about Desmos is it understands that. Now, TI-84s, they can handle parametrics also. I wouldn't say it's like difficult to do it, but you got to change modes. You got to do stuff like that. It doesn't give you the nicest looking graph. It's certainly not copy pastable. You know, there's no share links on a TI-84, and the TI folks, they're very resistant to making their calculators online platforms. They'll do the emulator thing, but they don't want to make a TI-84 into something like Desmos, because then they don't make as much money, right? So what we're going to do is go with the free thing that actually works better than the TI stuff. So I'm going to type in 2 rad t, comma, and I'm going to kind of reinforce that idea throughout the semester by repeatedly telling you all the different ways in which Desmos does something better than the TI calculator ever would. All right. So 2 rad t, comma 3t squared minus 2t. All right. Now you'll see that it requests a domain. The default domain is 0 to 1. Maybe that's not what I want, but I have no basis of understanding. Like, is it supposed to be anything other than 0 to 1? They didn't tell us. So when in doubt, I go -10 to 10. Get a little bit more of a graph out of it. If you want to go further, you can. A little nifty trick. This is straight out of the unit P packet. If you put a value on the low side, call it A, and a value B on the high side, create sliders for those. You see it automatically. I'll do that again because I kind of did that quickly. Go back to 0, 1, get rid of these things. So if you put in constants for the bounds, Desmos will ask you if you want to make sliders out of those. Right? Anything that's not defined as a variable, you see right there, add slider. Do the same thing with a B. You tap on all, then you can define your sliders so that you can say, okay, well, I want this to go down to -10, or maybe I don't want it to, you know? And so let's say I want it to go from -10 to 10. It gives me this good looking graph right here. But maybe I want to see what the progression of the path is of the function or the curve as the low bound gets greater and greater. I can slide along. Nothing's changing there, and there's a good reason why. We'll get to that in a second. And then you can see here that I'm truncating my graph based off of the low bound. Right? So maybe I only care about a certain interval. Right? Now, as you look at this, you probably realize that I didn't need to start at any value that would be less than 0. And that would be because of the presence of the radical within the expression. Right? So that's something important, because even though the question didn't ask for it here, all those relationships about continuity and differentiability, those are all still fair game, right? So the idea that like a function could be discontinuous or non-differentiable is still something that we have to consider, right? So I'm looking at this, I'm looking at the x equation, and I'm saying t has to be greater than or equal to 0. Otherwise, the function, in this case, it is a function, does not exist, all right? But it's also possible that there's another, kooky aspect to the equation in y, in the parametric. So maybe there's a natural log in there. Maybe there's a, like an absolute value function that has, some weirdness going on. Right. So a lot of things that need to be taken into account, because if you have the corner, the cusp, the vertical asymptotes, all those things, that they're still fair game. So all that Calc 1 stuff is still gonna come back. So, I've heard people say in the past, and I don't know how much I agree with it, but to some extent, they thought that Calc 3 was an easier course than Calc 2. I would say yes and no. Yes, in that there aren't a whole heck of a lot of new skills that we learn in this course. It's more like we're doing a lot more with the skills that we know, right? And so that's what makes it tricky. In Calc 1, Calc 2, it was like, all right, what do I do? I'm not sure. Take the derivative, set it equal to 0, and solve. That's probably the right way to go. Here, there's a little bit more thinking involved. All right. So that's where the practice comes into play. Right? Making sure that you spend the time to go over this stuff. Number 2, given the parametric equations, a little trig function there for you. Write the equation, or write an equation of the tangent line to the curve at the point where t is equal to 3 pi over 4. You'll notice I use the word an. Write an equation, and that's kind of like my go-to, because parametrics, the way they work, you could actually have multiple tangent lines at the same t value, depending on how it plays out. Right? There's some pretty crazy looking ones there, because we extend beyond the world of function related math. Right? So it can get a little crazy. So we just got to be mindful that there can be more than one. Right, but here I'm saying we only need one, so that's fine, right? Given the parametrics, okay. So dy dt, all right, so we're focusing on this guy first. So derivative sine cosine, so 3 times the cosine of t. We need a dx dt. All right, the derivative of cosine is negative sine, so negative 4 sine of t. All right, now when we come up with the dy dx here, we know that it's going to be the ratio of those two values here, or those two expressions. It's just a question of what you want to do with that. And I leave it up to you, because like I said before, I'm not going to tell you to simplify. It's just you're going to decide whether it's worth it to simplify based on what you see, what you observe. Now, we need to evaluate all of this stuff when t is equal to 3 pi over 4. Okay, not too bad. It's unit circle trig. So if you know your unit circle trig, you're in pretty good shape. The issue is, if you simplify the cosine over sine, that makes it a cotangent. If you don't know the cotangent of 3 pi over 4, don't put cosine over sine in terms of the reciprocal function cotangent. Just don't do it. Leave it as cosine and sine, because odds are you probably know that one a little bit more. All right. So in terms of the equation of a line, it's still going to be your good old-fashioned y equals mx plus b. It's just a question of whether it needs to be represented in parametric form or in rectangular form. All right, and it doesn't matter. That's another reason why I say an equation of the tangent line, because I'm saying it irrespective of the form, but I'll write it both ways. Okay, so you can write your good old point slope form, y equals m times x minus x sub 1 plus y sub 1. Right. Now, many of you know that as y minus y1 equals m times x minus x sub 1. It's the same thing. It doesn't take too much to see that if you just add the y1 to both sides, you get this one. But this one makes more sense, because we want to solve for y in terms of x, And also it's consistent with every other standard form of every other function that exists, right? So I need the slope and I need a point. Or I could say I need the point and the slope to make it consistent with the title, all right? So I need dy dx when t is equal to 3 pi over 4. I also need to know what x and y are at 3 pi over 4. All right, so comes a matter of evaluating functions. All right, so I'm going to pop in a 3 pi over 4 for cosine. All right, cosine of 3 pi over 4 is second quadrant. Cosine's negative in the second quadrant, so 4 times negative radical 2 over 2. So it's going to be negative 2 rad 2. Sine, so this is 3 sine of 3 pi over 4. And I'll show you the Desmos way of doing this in a sec. So 3 times, sine is positive in the second quadrant, so 3 times radical 2 over 2, positive, which would just be 3 radical 2 over 2. Then for the slope, I need this expression replacing, if I can speak, replacing every t. I'm going to bring it in a little bit with a 3 pi over 4. And again, if you know your cotangent relationships, which again are just the reciprocals of tangent relationships, and for 45-degree reference angles, that's the best case scenario. Then you don't really have to do a whole heck of a lot here. But I'm just going to assume that not everybody is unit circle ready at the moment. So we just kind of do it the old-fashioned way. So 3 times negative radical 2 over 2 over negative 4 times positive radical 2 over 2. Kill the negatives, kill the rad 2 over 2s, and get a clean 3/4. All right. So the one thing, it can be a little weird, but the x of 3 pi over 4 and the y of 3 pi over 4, that's me evaluating the original functions. So that's this one and this one, even though it's written right next to the dy dt and dx dt. I've had some people in the past say, I don't know, how'd you get a 4 cosine 3 pi over 4? It says 3 cosine right next to it. That's not where I was getting it from. All right. So then all I have to do is plug it on in, and I'd be looking at my tangent line equation. So 3 over 4, x minus whatever the x value is. So x minus negative 2 rad 2, so plus 2 rad 2. And then plus the y value 3 rad 2 over 2. And so this whole shebang here in its full glory would be the final answer, or one form of the final answer. I mean, you can simplify. You can write an equation of a line any way you want. I've settled on this method as being the way that makes the most sense mathematically, and also the way that will cause you to pull your hair out less than some of the other ways. All right. So yeah, a lot of stuff going on in this problem. Definitely a lot more than the last one, and we didn't even have to find a second derivative. All right. So then, two things. I want to show you how to check this on Desmos, which is actually really easy. But I also want to show you brain cramp. Oh yeah, another way to get these values. All right. So let's start off with checking it. Well, checking it, I'm just going to put in my my point slope form and see if it gives me something that looks like a tangent. If it doesn't look like a tangent, then I'm not going to be overly confident that I did this right. Okay, so I am not overly confident. So that means that I screwed something up. All right. Let me get 3 pi over 4. Oh, actually, let me leave that constant. Leave those sliders the way they are. Oh, this way. Backwards. All right. Quick double check. 4 cosine. That's good. Sine 3 pi over 4. 3 radical 2 over 2 plus. Then it's the derivative. Negative radical 2 over 2.
Is the parametric function in Desmos not the one for
Oh, thank you. Oh, dear Lord. I honestly, I would have spent the next 10 minutes trying to figure out where I flubbed this up. I really appreciate that. Thank you. Yeah, it helps to put the right problem in. And I don't need the X. Comma. Thank you. Thank you. 3 sine. And we'll do this on A to B because I still have my A and B sliders there. But you could already see that it looks good in terms of there being a tangent there. All right. Whew. So I get rid of this and get rid of that. And I'll just move this up and pretend none of that crap ever happened. Okay. Now, in terms of whether the domain is necessary, because this is clearly an ellipse, you know, a circle that's a little wider than it is tall. So it's got an oval look to it. Did I need to have a domain that goes out this far in order to create that ellipse? No, but also not really relevant, right? Because it was just a question of whether or not we had a tangent line based off of the information that we were given. So check. So that's good. Now what we need to do is figure out how, or not even figure out, it's just I want to show you how you could have done, you know, or gotten these values, or at least some of them. Because it's not going to, you know, just like a TI-84 wouldn't put something in simplest radical form for you, Desmos isn't going to either, at least not in most cases. There are some ways that it gives you irrational numbers, just not as many ways as you would hope. All right. So what I'll do is I'll just show you really quickly. If you take your original function and instead of putting in t, put in some other constant. I've already used a and b. Let me use c. And then add a slider for that. What it'll do is it'll create a point in space dependent on that relationship. All right. And you can even label it if you want. And honestly, in a lot of cases, you might want to do that. All right. So then what you can do is you can kind of scroll back and forth and you can see where that point falls on the graph. So how does that get you? How does that get you anywhere? Well, if I take that C value and make it 3 pi over 4, then it's going to present me with some coordinate values, right? And you can see them up there on the screen. You could also have it, you know, spit out the values for you too. But we're looking at about negative 2.8 and positive 2.1 as the X and Y values. Now, if you crunch those numbers, 2 radical 2 and 3 radical 2 over 2, you're going to see that they're equivalent, right? Because remember, we plugged in a negative 2 radical 2 in order for it to simplify to get the equation that we got. So we could actually get the values just by using kind of a modified form of the original parametric, right? So that's kind of a nice little tidbit. Now, the question that we get from this is, all right, well, that's all well and good. What if I need to have my answer in radical form? All right. Classic trick. Some of you are familiar with this one. This is old school. So you got this number, right? The negative 2 point, blah, blah, blah. And you know it's going to be a radical. You just don't know radical, you know, like what it is, the square root of. In Desmos, you can manipulate an expression. You figure that this is going to be the square root of something, then just square it and see. So if you get a funky decimal, if you don't know, like when push comes to shove, I'd love for everybody to know their unit circle stuff on the day of a test, but let's say you don't, and you're in a jam and you just can't remember, you know, it's like the sine of this, the cosine of that. You get the funky decimals when you use a calculator, but you know it's the square root of something. Square it, and then slap a radical on the thing that you just squared. The one thing you can't neglect is the sign of the thing that you squared, the SIGN sign. All right. So a quick example, let's say you need to figure out the tangent of 30 degrees. Well, it's in radian form, so pi over 6. And you're like, all right, well, I need a radical answer. So slap some parentheses around this bad boy and square it. All right, so it's radical 1/3. So that's 1 over radical 3. All right, so you can still get your radical stuff that way. And honestly, I probably should stop admitting this. That's how I got through 9th grade math. I did not pay to, like, I was one of those people that didn't believe that the unit circle would ever be that important. The teacher kept saying it, but I was like, yeah, I'm sure you're just making that up. You really think you're important. And so everything you say is stuff that I need to know. I'm not buying it. She was right, but that didn't stop me. I still got everything right because I figured out stuff like that. I was like, okay, the sine of 45 degrees, 0.7071. All right, well, it's the square root of something. Let's square it. All right. Got it. Square root of 1/2, simplify 1 over rad 2. Right. Rationalize if you need to, radical 2 over 2. And so there's little things that you can do along the way that make things easy. Right. Now, as far as making this into a different form, because a question could call for this to be a parametric representation. Right. So how would I write this as a parametric? I'll tell you, there's nothing easier in this course. I want to say in any course, that's not true. But in this course, there you will not find anything easier than writing a function equation as a parametric. It's the other way around where things get a little dicey. But when you're going from y equals something in terms of x, unless you're told what x is in terms of t, you get to decide on your own. I can define x to be whatever I want as long as there's a t in it. All right. So what I'm going to do is I'm going to say let x equal t. And what that means is that x increases. So x is a horizontal movement. It increases in lockstep with t. So for every 1 unit increase in t, there will be a 1 unit increase in x, right? Which is not really typical. Yeah, I mean, if you really think about it, like if you were to say that you're going to walk in a linear distance that's consistent with the elapsing of time, you would have to say things like, I am going to walk 1 foot every second. Probably too slow. All right, 1 yard every second. Okay, maybe. 1 mile every hour if you're defining t's in terms of hours. and it's kind of slow, I think, you know, so to get that balance is a little iffy, but you can define your X any way you want. And then once you have that definition, then all you're doing is you're replacing all the X's in your Y with T's, because now we know that X and T are equivalent to one another. I could say Y is equal to 3/4 T plus 2 rad 2 plus 3 rad 2 over 2. All right. So then you would say, okay, well, how does that equate? Will that get me a graph? Well, you're dang right it will. It's just not going to look pretty. All right. So let me show you. I'll get rid of this extra fluff because I don't want to make things too messy. But I can take my linear equation, I'll duplicate it. All right, that little double page thing. You hit that little gear thing, a little gear, and then hit that little double page thing to duplicate. All right, and then you can modify the thing that you just cloned. All right, so I'm going to get an ordered pair out of this. T, comma, and then replace the X in here with a T. All right. And so the question would be, is that the same thing? Well, kinda. It's hard to see, but there's this little smidge of boldness here. Just in this neighborhood right here, where it got a little darker. I can show you a little bit better. Turn one off, turn the other one on. They're parallel. If you want to make it more expansive, then change your domain. Make it like -10 to 10. So both going to the same place. But then the other question would be, okay, well, what if I decided my X was going to be equal to 2T? All right, well, you're not going to be wrong as long as you make the appropriate adjustment in your Y component, replacing your Y with a 2T. All right, and so you'll see here, same deal. All right, equivalent relations. All right, so no matter what you choose as your X, let X equal whatever, as long as it involves a T, you're going to make that same substitution into Y and everything's going to be fine as long as it's linear. All right, so your two components need to be linear in order for it to play out the right way. All right, if you decide you want to throw in a trig function, I mean, it'll still work, but now you're throwing in an inverse trig function to make up for it in your Y equation. That's making life a lot easier. Easier? No, more complicated is what I meant to say. All right, so you could do it that way. You could also write it in polar form, but that's too much of a nightmare to even consider at this point. All right, so that would be your set of parametrics if you wanted to write them that way. All right. And so the last thing on this page would be points of horizontal and vertical tangency. It's Calc 1. It's a set of Calc 1 questions, but we're giving it a Calc 3 twist. So we have X equals T squared. And you know, I am fully aware that I don't make anybody feel any better by pointing out how much of this stuff is Calc 1. I'm just telling you that you have the skills to be able to tackle these questions. You just got to believe that you can do it. All right. So if some of it seems too hard at first, I can tell you it will get easier with practice. All right. But especially in the beginning of the course, when you start having that feeling of like, oh crap, I'm supposed to know all this stuff. You know, there is an adjustment period, but we get through it. That unit P packet is going to be a big deal for a lot of you. All right. So if a lot of this stuff with parametrics and stuff like that, you're like, I don't know what the hell you're talking about. Go to that unit P packet and really look at those parametric videos. It's going to make a big difference. All right. You know what? I apologize. I just saw that there's something in the chat. Oh, sorry about that. That was a question from a while ago. So the question was, how did you get the point of -2.82? All right. So when you, if you wanted to do this using the Desmos calculator in order to get your, and I'll just highlight them. These guys over here, the -2 radical 2 and the 3 radical 2 over 2. what you can do, and let me just get rid of some of this fluff because we don't really need it. What you can do is take your original parametric, duplicate it. I'm going to slide it down so it's kind of got its own little space to shine here. Replace the variable t with a constant. So replace variable with a constant, right? Because Desmos knows that t is a variable, but it thinks everything other than t, x, and y, and theta, those are all going to be constant. So anytime it asks you to create a slider, it knows that you're trying to put in a constant, all right? So what I would do here is I'd add a slider for c, and the benefit of doing it this way, and I kind of glossed over this, so I apologize. By making it a slider rather than just doing direct substitutions, is that if I needed to put in multiple values, I can do it using the slider, all right? But here, I want it to be a 3 pi over 4, so I could just type in a 3 pi over 4. So it's basically what's happening here is we're substituting in a 3 pi over 4 for each c in the ordered pair. So then to get that to show up on the graph, we just tap on label here, and you can see that the coordinates are now based off of that value where c is equal to 3 pi over 4. All right. While I'm here, another way of kind of handling this, if you go with the slider approach, another like nifty technique that you can use would be, since this is a circular function, you can make this go from, let's say, 0 to 2 pi, pretty standard domain for a circular function, and make the steps something that's consistent with circular functions, like unit circle values. The basis of the unit circle is pi over 12. Even though we don't always deal with the pi over 12s, it's just every other value could be measured. That's the common denominator for all of the denominators around the unit circle. It's 12. All right. So if we pop in a pi over 12, then when we slide along, every little click along the way is going to be an increment of pi over 12. So then I could say I have 1 pi over 12. 2, 3 pi over 12, 4, 5, 6 pi over 12, which is the same as pi over 2. All right, so that's your 90-degree angle. Pretty easy to kind of check that one out. If you plug in a pi over 2 for cosine, it's going to give you a 0. If you plug in a pi over 2 for sine, it's going to give you a 1. 3 times a 1 gives you a 3. All right, so that's 6 pi over 12, 7 pi over 12, 8 pi over 12. 8 pi over 12 is 4 pi over 3. So 9 pi over 12 would be the one that we want. Yep, there we go. 9 pi over 12 would be the 3 pi over 4 if you simplify it. And that gives you the two coordinates. So -2 radical 2 corresponds to the -2.828. You pop that in. All right. And the other one, which is 3 radical 2 over 2, fraction first. 3 radical 2 over 2. That's something that takes a little getting used to. That's the 2.121. All right. What I was saying before is, if you're ever in doubt and you need to come up with a radical, just take the funky decimal, square it, and that's going to give you a sense of what the radical ought to be. Right, that's assuming that you don't know your unit circle stuff, but hopefully we'll get closer and closer to that. And, if I can just even go further afield here, I can say that if you really want to strengthen that unit circle stuff, do this just with a unit circle. All right, so the unit circle, and I can get rid of all this stuff here because we're about to move on to the next problem. Make it cosine comma sine from 0 to 2 pi, if I make my domain, again, going by pi over 12s. And you can see that these are the decimal equivalents of that unit circle, all right? So as you work your way around, and if you want, you just type in the equation of a circle with a radius of 1, just so you can see it. And then just trace your way around it, 1, 0, 2 pi over 12. Oh, let me zoom that out a little bit. 2 pi over 12 is the same as pi over 6. 3 pi over 12, which is the same as pi over 4, and so on. And now you have decimal equivalents of your unit circle values. All right. So there's a lot of good stuff that you can do with Desmos. You just got to get used to it. All right. So this is not meant to be me, showing off or anything. It's more so that, like, this is what you can do. Use it to your own advantage, because it will work out well for you. All right. Checking the chat. Yeah, no problem. All right, so the next one, find all points of horizontal and vertical tangency. All right, so horizontal tangent, going back to Calc 1 again, horizontal tangent happens when the derivative is equal to 0. All right, so the derivative, which is the slope of the tangent line, the slope is equal to 0. Slope of 0 means horizontal. So that's the cascading learning that happened right from Algebra 1 all the way through to here. You talk about that. It was the first thing we talked about in linear functions in 9th grade math, 8th grade, 9th grade math. We say, okay, well, which one is the 0 slope? This one. Which one is the no slope? That one. Which one's positive slope? Well, it depends on your perspective, but from my perspective, it's this one. And I don't know what it looks like on your end, but the other way would be negative. That's where it all starts. Same idea here. Whether it's polar, parametric, whether we get into three-dimensional stuff, it's still going to be the same idea. If we're looking for slope of a tangent line, we're looking for something that's horizontal. We're looking for a slope of 0 if it's horizontal. For a vertical tangent, that's the case of no slope, more specifically undefined slope, which would simplify down to just a nice clean 1 over 0. All right. So what I tell my intro to Calc students is think of it as 0 over 1 for the horizontal tangent and 1 over 0 for the vertical tangent. All right. It's just a flip. So what does that mean? We got to find our derivatives again. So dy dt. Nice power relation. So that's not bad. So 2t minus 3. dy dt, dy dt I already got, dx dt. 2t plus 1. All right. So let me clean up my Desmos and get those in. So, because we're going to need dy dx, which is the ratio of these two things, 2t minus 3, 2t plus 1. So original function t squared plus t. It isn't until you put the comma in and start typing in the rest of the parametric that that Desmos gives up and says, oh, you're not trying to put in a constant, you're trying to put in a parametric. So you just got to kind of believe that you're doing it the right way. All right. Now, again, the default setting is 0 to 1. I'm looking at my picture here. See a little fragment of a graph. I want more than just a fragment. I'll go -10 to 10. If I need more, I'll get more. All right. But based on what I see here, it looks like a rotated parabola. All right. Maybe a little bit of a translation of some points along the way, but that's besides the point. What we're looking for is a vertical tangent. I think I see one over in this. If I can get some points to show up. Oh, it's parametric, so it doesn't work out always the same way. But around that y-axis, 2, 4, 6, around between 6 and 8 on the y-axis, you can see it goes vertical there. So that's where we're looking for our vertical tangent. And then for horizontal, it looks like it's somewhere between x is equal to 2, 4, 6. Maybe it's right at 4. I'm not sure, but that at least we have an idea. you know, where to look. So what we're going to do is we can take our derivative, dy dx. We'll set that equal to 0. That's going to be for the horizontal tangent. So that's going to be 2t minus 3 over 2t plus 1. So that's going to be 0 over 1, cross multiply. We're looking at 2t minus 3 is equal to 0. You know, subtract, divide, t is equal to 3/2. All right. So what I would want to do is verify that that's actually going to be the case. All right. So I like going with a constant to represent the point. So I'm going to do that duplicate thing. I'm going to replace all my t's with c's. Doesn't have, oh, well, c squared. Replace all your c's with t's. Sometimes it's easier to just type it in again, but I didn't want to do that. All right, just double check that you didn't screw something up. That's really me directing that comment at myself. And then just take a look and see where we're at when c is equal to 1.5. And, you know, sometimes, because I'm using the touchscreen here, sometimes as much as I try to get it on that perfect 1.5, it just keeps moving on me. And when that happens, I can either persevere or just give up and tap in. One's not better than the other. They both work the same. Right? But that does look like it's a horizontal tangent. Right? And from there, I get some nice coordinates for a change. So 3.75. I mean, our derivative, I'm sorry, the original function, I mean, it's got some powers in it, but it doesn't have any funky radicals in there. So there's no reason for me to think that the coordinates would be anything, you know, that just rounded to 3.75. They probably are 3.75 and 2.75. So what I can say here, because if I'm looking for coordinates, I got them. 3.75 and 2.75. If you want to go fraction form on that, by all means, go for it. Right? You can also, if you want to, there's another little nifty approach to things. Oh, you know, sorry, forget I did that. Ignore me. That I was thinking of GeoGebra. We'll get to that. Yeah, there's the other platform we're going to learn about. If you do a computation and define it as a new variable, and then write that new variable in a new line, it'll spit out what the value is at that new variable. That's going to happen, unfortunately, pretty frequently with me, where I get GeoGebra and Desmos confused. All right, so let me just see here. What do we got in the chat? Yeah, it would still understand 3/2. Very good question. Yeah, so you don't have to put it in as 1.5. If you tap into the field and put in 3/2, it'll know what you're talking about. So 3 divided by 2, and it automatically changes it to 1.5, but then it still does the computation for you. Good stuff. All right. So we have the coordinates for the horizontal tangent, and this is going with the theme of it's not an algebra course. So yeah, could you plug in a 3/2 into the t squared plus t and the t squared minus 3t plus 5? Yeah, I have every confidence in your ability to do that. Couple of things. One, I don't want to have to read that work when I'm grading your papers. That's a little selfish on my part. Two, I don't want to have to take off points if you screw it up when you do it on your papers. So that's the generous part, right? So I don't like taking off for algebraic mistakes in a class that does not have algebra in the title. Right? I think if you really think about that, it should sound reasonable. If you don't, we can talk more. But I've had people say, well, you're not doing math unless you're doing it by hand. And I would say, do me a favor, go look up the definition of mathematics and then get back to me. Right? So dy dx is equal to 1 over 0. So 2t minus 3, 2t plus 1. All right. And actually, if you look up the definition of algebra, you see that not a lot of the stuff that you do in an algebra class technically fits the definition of algebra. But that's enough of that. 2t plus 1 cross multiply is equal to 0. And so t would be equal to negative 1/2. And so you could do the same thing here. Whoa, that was crazy. I hadn't tried that in the Desmos interface. It didn't really work with the Apple Pencil, but whatever. Good to know. So you can pop in the negative 1/2 and see what that gives you in terms of a point. We do want to verify a couple of things. One, that it actually gives us a point on the curve, not some point that's like at a discontinuity. Because again, just like in Calc 1, if it doesn't exist at that point, it's not going to have a vertical tangent at that point. All right. So that's something to be mindful of. Also, maybe it's part of a graph that's not relevant. You know, so in this case, we weren't given a domain. We weren't given a restriction to the domain, so we don't have to worry about it. But if this said only focus on values of x greater than or equal to 0, then we would disregard this. All right, so that's something you got to keep in mind. But it turns out neither of those things are relevant in this case, so we're good to go. So negative 0.25 or negative a quarter if you want, comma 6.75. All right. And so you got your horizontal tangent, you got your vertical tangent, but it all comes down, if you really think about it, looking at the skills that we're talking about on this page, it's just a skill related to finding the derivative of parametrics. Now, some of us are kind of getting up to speed on parametrics to begin with. That makes things a little juicier, but I always am mindful in the beginning of the course not to slam you with too much in terms of applications of parametrics before you got in your footing when it comes to understanding parametrics to begin with. All right, so definitely if a lot of this is like I know I've seen it before, it's just not fresh, then go back and take a look at that unit P pack. It'll do wonders, or at least in my mind it does. All right. We are going to flip back to the previous page now and talk about, when we talked about derivatives, so now let's talk about antiderivatives. Let's see what we got in the chat. Oh, why is the negative? Why is the 1/2 negative? That's because if you evaluate the function, the x equation, for where t is equal to negative 1/2, you're going to get a quarter plus negative 1/2. And so that's going to give you a negative 1/4. Right.
Professor, if we change the parametric equations to rectangular equation and get the derivative of that, like dy over dx, can we still solve the problem in the way?
You can, unless the directions to the problem say to use a parametric approach, right? So you got to be prepared both ways. But yeah, if it doesn't say one way or the other, you can go any way.
Okay, thank you. I was just curious.
Yeah, good question. Honestly, either way are fine by me because of the skills involved. As we go forward, you'll all see that there will be some instances where you'll start to prefer parametric form because the rectangular form is just so nightmarish. But this one really isn't that bad either way. Okay, so let's flip on back and take a look at this baby right here, arc length in parametric form, because you're looking at this curve right here and you're saying, you got to be thinking, gee, I wonder what the length of that thing is, specifically from A to B. No, I mean, I don't know that thought crossed anybody's minds until I brought it up, but it will, because a lot of the things that we're going to do as we go forward through the course is going to be reliant on the concept of arc length. you're going to find that comes up over and over and over again. In fact, we'll learn how to parameterize in terms of arc length, which is like, what? Well, now you're just making stuff up, dude. And I agree. It sounds like that even when the words come out of my mouth. But the analog to that is if you have, let's say, you got a mountain. I don't know how to draw a mountain, so I'm gonna just draw a mountain. All right. And on that mountain, you have a windy trail. Okay. And you have some point that's moving along that windy trail. Traveling along, traveling along, traveling along, and eventually gets to the top. And then starts coming back down. All wonderful stuff. And if it's like Haleakala and what was that, Maui, been on that bus ride to the top, that like hour-long bus ride. I thought I was going to die at every turn. Yeah, some drives are a little longer than others. Some people walk up those windy roads. Some people cycle up them and down them, and it's all exciting, right? So what can happen is your distance, let's say you have an observer that's on the ground over here. Some guy, he's happy because he doesn't have to be on that bus ride. He's got his line of sight. That's not a line. Got his line of sight to your position. But then you move along and his line of sight changes. If I could turn my line draw tool on. And then, maybe you get over here, line of sight changes. And, for every one of these points, I can do a little duplication action here. Oh, that's not duplicate. Copy. Paste. You're over here. You're over here. And, just so I don't spend the rest of the class time drawing a terrible diagram, I'll do one or two more. I guess I need to actually use my lasso tool. So he's over here and he's like driving along, eventually gets to the top. All right. So we got all this information, but that information is solely related to that individual's perspective. All right. That person here could be considered a fixed point. All right. Now that fixed point maybe, for example, is the origin. Call that the origin. All right. And every one of those points, and I can just kind of highlight one of them. It doesn't, it doesn't matter which one I highlight. I'll go green for those cubes scored home. Every one of those points is going to have a horizontal and vertical component that we call X and Y. That's nothing new there. With an appropriate hypotenuse, and then we can do all our trig related to that. All right. Now, the big question is going to be, well, all right, that's cool, but that means that everything is relative to a fixed point that's not on the path. What if the point that we're talking about is another point that's on the path, and that point is immediately preceding the point of interest? All right. So for every step that I take along the journey, I'm always relating it back to the point that came before it. So I have all these points along the way. And instead of saying what's happening in relation to that point of origin, I would say what's happening from this point to this point. And then from this point undo, to this one, and then to this one, and then back to this one, and so on, all the way around the through the path, which we haven't learned how to create yet, because this would be a curve in three-dimensional space, because it's going to have height. But we would have to come up with a method by which we can categorize all those little tiny distances along that curve, because no longer would we be interested in that fixed point. That fixed point at the origin, that's a two-dimensional way of thinking, specifically related to rectangular coordinates. Now we want to get into three-dimensional ways of thinking and allow that to relate not just to some fixed point in space, but to an ever-moving point, right? So instead of me saying, how far have I gone from the base lodge? It's more like I'm going up a chairlift on a, I'm going skiing, I'm going up the chairlift. What's my position relative to my position 10 seconds ago? Not my position relative to the cafeteria where they have a really good mountain chili, right? So that's two different ways of looking at things. This idea, the idea of finding arc length, is going to be crucial in terms of understanding that. All right. So we want to take our time. Oh, excuse me, but we want to get to a point where we really have a good understanding. Right. So there's some formulas. There's always formulas. I can give you formulas. I saw online somewhere that somebody had like this big formula sheet for Calc 3 stuff. And I was like, oh, that's great. And I looked through it and I thought to and it was like somebody wrote really small, and they took up like a whole page of paper and they color coded everything. And at the end, it was like, oh, they just wrote formulas. There's no real like thinking involved in that. And that works for a lot of people, I guess. But as I was looking through it, I kept thinking to myself, I'm like, well, I don't need to know that formula. I can figure that out if I understand this. If I understand this concept, I can figure out that formula. So half of this stuff I don't even need. That's kind of what I'm going for when I explain these concepts. I'm going for understanding rather than rote memorization. So, we have memorization to fall back on, but understanding is what we're going for. All right. So when we talk about arc length, we're talking about a little tiny little segment, little smidge of a segment that exists on an interval. All right. And instead of saying, you know what, what's the length of this whole curve? Let's find the length of a little tiny little smidge of the curve. And then once we're done with that, find the length of another tiny little smidge of the curve. And then once we're done with that, find the length of another tiny little smidge of the curve, and so on, and then put it all together after the fact. But just like in Calc 2, when you had to come up with like volumes of revolution and things like that, it wasn't just a matter of saying, okay, well, that's great. Let me just, I guess, throw a ruler on this. You can put a ruler on it and measure those little tiny segments. I remember those activities back when I was in elementary school where they give you a map and they say, how long is the curve? So you get the ruler and then you measure, and then you say, okay, well, this part's kind of like a line, so let me measure that little piece. All right, that's like a quarter of an inch, right? A little bit more, I can get this stretch. All right, it's a little off, but that's about an inch. And then that, and then that, and that, and that, and you add it all up, and you're like, okay, that's about 7 inches. What does that correspond to in the scale at the bottom? The little key, the little legend. And then you get a rough estimate of what the distance is between Buffalo and Cleveland. This is kind of like that, but we do need an expression to represent that little tiny smidge of distance. So that's where this is, the little minute section of the curve will have some distance that we call ds. All right, so this little distance here, a little smidge of a distance, we call that ds. All right. So the relationship between dx, dy, and ds is going to be Pythagorean. And that's an important revelation or realization. Because if we say, okay, well, any kind of line segment or a curve in space can be decomposed into horizontal and vertical components, then I can say that dx squared plus dy squared is equal to ds squared. All right. And so by extension, you just by taking the square root, I can say ds is equal to the root of what I just wrote. If my pen wants to work, there it is. All right, but somehow we have to come up, well, a couple of things. We got to come up with one of these rules here. That's not as important as saying, well, we got to come up with a relationship that'll allow us to determine the length of a curve over an extended interval, not just in a minute little region. All right. So one thing that we can do is kind of look at this as a rate and just make all our dx's and dy's, the ds's into dx dt, dy dt, and ds dt, because we could say that this is happening per unit of time. So that's one way to handle it. Another way to handle it, which is my preferred way of doing it, is to say, well, why don't we multiply both sides of this equation by a dt? Okay. If we multiply both sides of the equation by a dt, then what we're doing is we're establishing that we're getting a length of a curve over a minute interval of time. All right, so we would get that minute interval of time, ds dt, and we can redefine that as some new variable. Like we have a lowercase s here, so we can call it an uppercase s. All right, we can call it something else if we want. All right, but what that allows for us to do is to say, you know what, I want this to be a collective interval. All right, so that's one way of handling it. And then once we have that, I can say, for example, let ds times dt be equal to, I'm going to make it a capital ds, or well, a capital S, right? And so that's going to be equal to my right-hand side. I can get rid of the multiplication symbol because eventually we're going to have an integral out of this. So, you know, and part of that integral is going to involve a dt, so we're in pretty good shape there. So now it's just a question of, okay, well, where on earth are those other dt's coming from? Well, there's a couple of ways to handle that part of it, right? One way would be really to just kind of introduce them, right? But another way would be to, like I was saying, go back to what I was saying before. So let's say, and I'm just going to grab this, I'm going to kind of work the two concepts simultaneously. Draw a little line here. Let's say I wanted to go the route I think the explanation works better if there's like a side-by-side thing going on. All right, so I'm going to say dy dt, dx dt, and ds dt. All right. So for this concept, and like I said, I'll come back to the one on the right because I want to show you the thinking on the left and then use that to kind of bridge the gap and help you understand what's happening on the right. So just focusing on this, we're looking at dx dt squared plus dy dt squared is equal to ds dt squared. All right. And the idea here is that if we have some sort of horizontal change, infinitesimal horizontal change, we might say that that's per some infinitesimal unit of time. All right. Now, if I square the left-hand side, then I'm kind of working against what I want to do, because if I'm looking at the rules that I have above, I see I have a dx squared and a dy squared, so I'm going to leave that alone. So on the right-hand side, I can square it, but I also see that I'm supposed to have a radical in there, so why not take the square root of both sides? At which point, left-hand side stays put, but the right-hand side becomes a ds dt, just a clean ds dt. I don't need that part of I don't need the equal sign. Already had it. Resize a little bit for some space. All right. So if I want ds alone, I would just multiply both sides by dt. And let me zoom out a little bit, and you'll see that that's pretty much what we have here, except we don't have the integral. All right. And so what we're looking at is the part of the expression that gives you, if you reference this in terms of time, it gives you just that little smidge, a little tiny smidge of curve, where if we were to integrate it over the length of some interval a to b, then we would have the complete arc length. All right. So I'll call it a to b. Some interval a to b. On the left-hand side, it just becomes s. And on the right-hand side, it's the whole expression. All right. So that's the one way in its complete form, but that doesn't really get at the idea of why we divided by dt's to begin with. All right, and so that's where the other explanation comes into play, which is kind of a better one. Just trying to clean this up a little bit so it's not crap. I mean, it's already like dangerous territory here. Like the in-class equivalent is, you know, when the teacher, it usually is me, writes so big in the beginning on a board, like a whiteboard or something, and then paints themselves into a corner where they have no room to write anything else. Yeah, I did that just now. And you saw what that looks like in a digital form. So I was so concerned with my little mountain there that everything else kind of fell by the wayside. Oh crap! Something. So I guess I'll just give the shorter version here. If I want to get to a point where I can simplify the one into the other, one way to handle it would be to take this expression copy, paste. So I'll just kind of work with this. Take this expression and simplify it until we get to this point, but that's kind of not the idea behind everything. What we'd rather do is clean things up a little nicer. And you know what? There's a benefit to doing this let statement that I had before, but you know, just to keep the the terms consistent, I'm going to go back on that and just say, so I'll get rid of this and just go with the original ds. I'll talk more about the benefit of making it the capital S in a little bit, but for now, let me just go back on that, because I'm going to leave that ds dt here. And it might not seem like it's a useful step, but what I'm going to do is I'm going to divide both sides by dt. And you might say, well, that's not helpful. Why would you do that? That's terrible. El terrible. If I can get the friggin' line to work out right, I'm just going to hand draw it. All right, but what I can do here on the left side, clean it up just by simplifying. I'm going to get rid of this arrow. It looks ugly now. A better looking arrow. That's going to give us just the ds. Now on the right hand side, I'm going to write this. So let me just bring it in a little bit. Instead of a dt, I'm going to write that as the square root of dt squared. So it may have seemed at first like I was going to use that to cancel out the dt on the right hand side, but that would have defeated the purpose. Okay? If I did that, then I wouldn't have my dt anymore, and I need the dt. Okay? So on the right hand side, I can now bring that dt squared into the radical. And if you split up your fractions, we're looking at dx squared over dt squared plus dy squared over dt squared which in turn becomes dx dt squared plus dy dt squared under the radical dt with that ds in the front. All right. So I could have, because there's another variation, and I was getting a little ahead of myself. There's another variation of the arc length formula that we could use, that where you could do the ds times the dt. I was going to go down that road, and I decided not to, because it would have made things too complicated at first. But as we went. But you can see hopefully that we're looking at the same expression that we had before. It's just a matter of saying, all right, well, now I want to integrate over a to b. And when I do that, I finally, at long last, get that thing that I had teased before. Barely left myself any room for, but it ends up being equivalent. So it's two distinct proofs for the same rule. And you look at it and say, well, first off, there's got to be the classic, is this going to be on the test? So I'll get to that in a second. And then the other one of, okay, well, which one would we have to know if this is on the test? So the answer to the first question is yes. Whenever I introduce a proof in class, it's fair game for a test. I put 10 questions on a test. One of them is always a proof, right? And so it could be, so far we've learned 2 of them. I've shown you a really simple one, which is how to come up with the first and second derivative. Not really so much the first, but the second derivative. And also 2 ways to come up with the arc length formula in parametric form. I'm also going to show you how to do it in polar form next class. So more on that later. But when it comes to how you choose to prove something, it doesn't matter to me. It's just, I like both of these methods, and yeah, do I regret doing them simultaneously? Kind of. If I had to do it all over again, I would have led with the one I did on the left and then said, oh, here's another way to do it. And I apologize if there's any confusion. But there are 2 complete proofs. It's just, I think the one on the right, and I think it's probably a little bit more confusing than the one on the left, it doesn't have that mystery of how the dx, dy, and ds just somehow becomes dx dt, dy dt, and ds dt. I think there's a lot of hand waving that goes on there, where you say, well, if we just think of it as happening per unit of time. And so if I was a student, it'd be like, okay, well, that's a hell of an assumption to make. Why are we allowed to just think that? The proof on the right of that vertical line where I say ds times dt, that if I'm taking a little infinitesimal distance, and then I'm saying, okay, but I want that to happen not just for 1 second, I want it to happen for every little infinitesimal change in time, that gives me an accumulation of distances. I think that makes more sense. All right, if I tell you that I'm going to travel 1 foot in 1 second, and then I say, well, how many feet am I going to travel in 30 seconds? You know you're going to be multiplying those two numbers. The proof on the right gets at that, but it involves more steps. When it comes to the test, I don't care which one you do. The goal is that you start to develop a more intuitive understanding of the concept of arc length, because I know in Calc 2, it was like, here's the formula. Can you get the arc length? Good. Congratulations. You can now move on to Calc 3, where you'll worry about why you need to do that. Now we're at the point where we need to worry about why we're doing it. All right. Sorry, it's 8:01. I apologize. It breaks my heart if I ever go over time, because it's not cool. So I am going to stop the recording if this dang thing will let me.